Hello everyone, this video is on normal subgroups. Normal subgroups are very important type of groups. First we discuss the motivation behind the study of normal subgroups. Quotient operation AHBH equals to ABH. This quotient operation it was well defined for subgroup H. H is the kernel of a homomorphism. Now the question is it well defined for any subgroup N of G? Now the answer to this question it will lead us to the study of normal subgroup. Now let us take a closer look at H. For H we have BH2 equals to S3B for some S3 in H. This is true for all S2 in H and for all B in G. And because of this, AH1 BH2 equals to AH1 S3B and that equals to AB S4 for some S4 in H. And because of this, the quotient operation AHBH equals to ABH was well defined. So, what property of H led to the well definedness of the quotient operation of H? This property of H. So, for any subgroup N of G, if N obeys this property, that is, for all N1 belongs to N and for all G belongs to G, Gn1 equals to N to G for some N2 in N, then N is said to be normal in G. Now we give a formal definition of normal subgroup. Let N be any subgroup of G, then if for all N1 in G and for all G belongs to G, we have Gn1 equals to N to G for some N2 in N, that is, for N, the quotient operation AHBH equals to ABH is well defined, then N is said to be normal subgroup in G, or simply normal in G. Now there are more than one ways to define normal subgroup. Gn equals to N prime G, or Gn G inverse belongs to N, or Gn G inverse equals to N, or the left quotient Gn equals to the right quotient Ng are some ways to define normal subgroup. Now we saw that all these definitions are equivalent to each other. Now we saw that this implies this. We have Gn equals to N prime G because N is normal in G. Now operate on both sides on the right by inverse of G. We get Gn G inverse equals to N, that it belongs to N. So Gn G inverse belongs to N. Next we show first implies second. We have to show these two sets are equal. So we show that these two sets are subsets of each other. For that, suppose N belongs to N. Then we have Gn G inverse equals to N prime belongs to N. Because this is given to us. Gn G inverse belongs to capital N. Then after simplification we get small n equals to G inverse N prime G, and clearly G inverse N prime G belongs to the set G capital N G, and this shows N belongs to the set G capital N G, and we have capital N is subset of G and G inverse. Also from first, G and G inverse belongs to N implies that G capital N G inverse is subset of N, and we just proved that capital N is subset of G capital N G inverse. So we have G capital N G inverse equals to N. So first implies second. Next we prove second implies third. We have to prove the left quotient Gn equals to the right quotient Ng. And we are given G capital N G inverse equals to N. So we have G and G inverse equals to N prime belongs to N. Now operate by G on right on both sides, we get Gn equals to N prime G for all N belongs to N, G belongs to G. And this clearly shows that G capital N equals to capital N G, and it is proved. Next we have a theorem that is related to homomorphism and normal subgroups. That phi from G to G dash is a group homomorphism, then N is normal in G implies phi N is normal in phi G, and N prime is normal in phi G implies phi inverse N prime is normal in G. That means phi, if it is a homomorphism, it carries normal subgroup of G to normal subgroup of phi G. That means phi it preserves normal subgroups if it is a homomorphism. Now we proceed to the proof. First part of the proof is N subset of G is normal in G is given to us, and we have to prove phi N is normal in phi G. We have phi G belongs to phi capital G and phi N1 belongs to phi capital N. Then we have phi G, phi N1 equals to phi gn1 by the property of homomorphism, and that equals to phi n to g, because n is normal in g is given to us, so we have gn1 equals to n to g for some n2 in capital N. We have already discussed that, and this gives us phi n to phi g. Then from definition, phi n is normal in phi g. Second, we have n prime is normal in phi g is given to us. We have to prove phi inverse n prime is normal in g. For that, we take any elements from capital G and phi inverse n prime. Let g belongs to capital G, that implies phi g belongs to phi capital G, and let n1 belongs to phi inverse n prime, and that implies phi n1 belongs to n prime. Now we have phi g n1 equals to phi g phi n1 by the property of homomorphism, and that equals to phi n to phi g, because n prime is normal in phi g, so we have phi g phi n1 equals to phi n to phi g, and that equals to phi n to g again by the property of homomorphism, and this shows phi gn1 equals to phi n to g, and that implies gn1 equals to n to g. Then from definition of normal subgroup, we have phi inverse n prime is normal in G, and the theorem is proved.